Okay, so only announcement I've got for today is that the chapter 19 is due Wednesday at 9 a.m. I originally set it to Monday and then bumped it forward to Wednesday, and it's sounding like I may not have hit save or something on that. So if it is showing Monday 9 a.m., you guys get an extra couple of days. I'll take a look at it once I get back to my office. Oh, I guess the other announcement I have is exam regrades are due noon on Friday. So those who've gone back to your TAs, you should be able to get it back in your recitation this week or by agreeing to meet up with your TA earlier, maybe during their office hours or something. Okay, questions about that? Yeah? Do we? I don't think so. I'm going to set the due dates so that they don't. Oh, yeah, I think when I set up the chapter 20, I just picked some date in the future, and I wasn't sure when we'd actually get to finish that. So I'll bump that due date forward, depending on when we finish chapter 20, which hopefully will be Wednesday. By the way, the 1 week after we finish the chapter thing, doesn't include the week of spring break. So if we finish it this Wednesday, I'll have the due date be 2 weeks in the future, the Wednesday after we get back. So, okay. So I am starting chapter 20 today, which the notes are posted for now. So chapter 20 is all about carboxylic acids. Okay, so we spent all of chapter 19 looking at things in the 2 bonds to oxygen oxidation state. So aldehydes and ketones are sort of the big two in that category. But we also looked at a bunch of derivatives like diols, acetals, hemiacetals, imines, stuff like that. In this chapter, we're going up a level on sort of the oxidation ladder, and we're looking at things with 3 bonds to oxygen. So I guess the parent of all of these is carboxylic acids, which are this thing as a reminder. It's a carbonyl but with an OH attached to it. But we're also going to be looking at a bunch of what are called acid derivatives, which are things in the same oxidation level. So one thing that's going to help sort of keep these ordered in terms of explaining their reactivity is this sort of ranking of reactivity. So on this end, I'm going to put most stable, or actually no, to match up with the notes, I'm going to put least stable on this end. Which in other words, it's saying most reactive, or in other words, biggest delta positive at carbon. And on this end, I'm going to put most stable, or least reactive, or smallest delta positive. Okay, so we're going to see 1, 2, 3, 4, 5, 6, 7, 8 things on this ranking. 2 of them are not actually acid derivatives. I'm just throwing them in from the last chapter because it'll sort of help explain some other stuff that we can and can't do from before. Let's see. Okay, so over here we've got acid chlorides. It's a carboxylic acid, only you replace the OH with a chlorine. We've got anhydrides. Which, if you look at it, it's actually like you took 2 carboxylic acids and stuck them together and removed a molecule of water, which is where the name anhydride comes from. So if we added water back into this thing, we'd get 2 things of carboxylic acid back out. Okay, so I'm going to throw in aldehydes and ketones from the last chapter just so we can look at where they fall in the rankings. Okay, so these 2 are not acid derivatives. I'm just throwing them in here. Okay, and then we've got acids themselves. We've got esters. We've got amides. And in the notes, I have this as NR2. Really, either or both of those R's could be replaced with H's, and it would still be an amide. And then we've got nitriles. Way over here. Okay, so this is the only one, the nitrile, that doesn't explicitly have a carbonyl in it. Like there's no double bond O. But if you look at it, it's still carbon with 3 bonds to a more electronegative atom. So it is still in the same family of acid derivatives. It's just, it's the only one without an oxygen. And also because there's no double bond between carbon and oxygen, it's got the smallest delta positive. So this thing is pretty stable and unreactive compared to the other ones. Okay. So any questions about that so far? Okay, cool. So hopefully all of these look pretty familiar from like when you learned functional groups earlier or from lab. But just to sort of put them up here by actual rankings of delta positive. Okay. So one thing that's worth noting here is that a lot of the chemistry we learned on aldehydes and ketones from before is not actually going to work on a lot of the things in this chapter. So like these are more reactive and we can do things to them that we couldn't actually do to acids and esters. All right, so we're going to cover some cases where we can do the same or similar chemistry. But in general, if we covered it in Chapter 19, probably pretty safe to assume that it's not going to work the same in this chapter. Partly that's due to lower reactivity for a lot of these things, and partly that's also due to all of these have some kind of leaving group attached to them, and that's going to change the outcome of the reactions. Okay, so we'll go into detail on the exceptions to that. Okay. Okay, so in terms of why things are ranked this way, a lot of it just comes down to kind of similar trends to what we saw for aldehydes and ketones. Basically, the more assistance the carbonyl carbon is getting in stabilizing its positive charge, the happier and more stable it's going to be. So let's pick out a couple to use for examples. So acid chlorides here are the most reactive. You may remember chlorine, when we saw it in the electrophilic aromatic substitution chapter, was sort of canceling out its own effects. It was electron donating by resonance, so like it could take its lone pair and kick it in towards the carbon, but it was also electron withdrawing by inductance. So even though it can officially throw some electrons at it, overall it's taking more than its fair share of electron density out of that, And so it's actually electron withdrawing overall slightly, which is why it was deactivating in the EAS chapter. So this thing is actually increasing the size of the delta positive. And you're getting a pretty big plus charge on that carbon, like bigger than it would be otherwise. By contrast, if we're looking at, say, carboxylic acids, we know that the OH group in EAS reactions was electron donating overall. That's because it does still have a dipole going on. It is pulling some electron density towards itself, but it's also kicking in electron density by resonance, just like the chlorine is. And in the case of oxygen, that resonance happens to be sort of a bigger factor. So this one can actually sort of reduce the size of the delta positive. So chlorine is electron withdrawing because its inductive nature wins out slightly. OH is an electron donating group overall. Just because the resonance happens to be the stronger effect. Okay, so that's why it's a smaller delta positive than, say, aldehyde and ketone, which don't have resonance stabilizing their delta positives. Okay, and then if we go like further over to the right here, if we have like a nitrogen, that's also strongly electron donating by resonance. And it doesn't really have that much in the way of inductance either. So even more electron donating group by resonance, because this can also do the same thing. Oh, I guess I should show both arrows if I'm doing resonance. Okay. So this one has a teeny, relatively, delta positive on the carbon. Okay. I guess I didn't draw it up here, but anhydrides, you might be asking, like, why aren't they just as stable as acids? Because we do still have an oxygen here that can kick in by resonance to one side. But the problem is that central oxygen is actually being split between two carbonyls, and so it just can't donate electrons by resonance as much as like the one OH here can to the only carbonyl it's got. Okay. Any questions about that? Okay, cool. So just like the previous two chapters, we're going to spend a little while on nomenclature, but not very long. Just enough that you can recognize what the questions are talking about if they give you a name. Okay, so naming stuff is actually real similar to aldehydes, which makes sense. It's sort of a terminal functional group on the chain. Okay, so instead of dropping the terminal E and adding al like we did for aldehydes, we're going to add oic acid. So OIC acid to the end. And the carbonyl carbon is going to be carbon number 1. And then you can name whatever other substituents like necessary. I guess if you've got a diacid, then you then you're going to keep the E, just like you did for dialdehydes in the past. And you're going to add dioic acid. Okay, so some examples here. This one would be 1, 2, 3 carbons, so it's propane derived, so it's propanoic acid. This one has 1, 2, 3, 4, 5 carbons. It's pentane derived, so it's a diacid, so it's pentane dioic acid. Okay, questions about those two? Okay. You may notice that I pretty much copy-pasted these examples from the previous chapter. I just turned them all from aldehydes to carboxylic acids because it's that similar. Okay, so just like with aldehydes, if you can't include the carboxylic acid as part of the parent chain, but that carbon is directly attached to the parent chain, you can sort of name it as a substituent. So if the COOH group, the carboxylic acid group, is directly attached to the parent, just add carboxylic acid to the end of the parent name. Just like when we added carbaldehyde to things with an aldehyde substituent. So this is most relevant in cases where you can't include the acid carbon as part of the parent, maybe because, you know, it's attached to a ring or something like this. So this would be cyclohexane carboxylic acid. Or you can do it for multiple groups on the parent. So like this, the parent's going to be benzene, but it's got 3 acid carbons coming off of it. So you would name this as 1, 2, 4. Benzene tricarboxylic acid. Okay, so questions about those examples? Okay. All right, so in terms of principal functional group ranking, carboxylic acids outrank everything we've seen before, everything we've seen so far. Okay, so they take priority over aldehydes, which take priority over ketones, which take priority over alcohols, which take priority over thiols. Okay. So a few non-systematic names that I'm going to cover real quick. There's a ton of them because some of these were actually the first sort of organic compounds to be really well systematically studied, but the ones that we're most likely to see are actually some that we've used fairly frequently in lab. So this one under IUPAC, it's ethane, so ethanoic acid. But that's not what anyone calls it. What is that? Acetic acid, yep. Okay. And then a couple more that might come up are some diacids. So this one is oxalic acid. And this one, which we're going to see a bunch of derivatives of a couple chapters from now, is malonic acid. Okay. Any questions about those ones? Okay, cool. All right, so that's it for naming. That's pretty much the only extent we're going to look at it. What we're going to do now is sort of take a quick, I guess, refresher and look at acidic behavior of these molecules, because that kind of dictates a lot of what they do. And we're also going to look at some similar functional groups that are acidic for the same reason. Okay. So the whole reason these things are called carboxylic acids as a functional group is because, not surprisingly, they lose a proton very easily. But the reason that's the case is just like we've always seen for acid-base equilibria, it all comes down to how stable is the conjugate base with a negative charge. So this thing is quite stable with a negative charge because we know that we can do resonance and move that charge around to two different locations in the molecule. So its conjugate base is pretty stable, so the starting material, the carboxylic acid, is fairly acidic. Okay, so if those of you who had me for OChem 1 or who have looked through the OChem 1 notes, there's this acronym that's CARDIO, discussing the 5 different factors that affect pKa's in molecules. This one is all or largely due to the resonance effect. Turns out there's also a little bit of dipole induction going on, just because the carbonyl here gives it a delta positive, which helps stabilize the negative charge a little bit. But the biggest factor is resonance. Okay. So this was actually the functional group that we first looked at when we were explaining the inductive effect too, because we can throw some groups onto the far end of the molecule out here that will stabilize that minus charge even more and make the molecule even more acidic. So to throw some examples up here, so just straight acetic acid by itself has a pKa of 4.76. If we take the same molecule, throw 3 fluorines onto here, this is Trifluoroacetic Acid, TFA. Its pKa drops all the way down to 0.23. So it's way more acidic, just because these 3 fluorines out here are helping to pull charge out towards themselves. So as soon as this proton leaves, this minus charge is way more stable than it would be otherwise, or a fair bit more stable, about 4.5 units more stable. Okay, by contrast, if we throw something out there that destabilizes the negative charge, say like something with an entire minus charge on it, this is going to be pushing some electron density back this direction, which means that if we try to take a minus charge on over here, that's going to get a lot less stable than it would be without the O minus. So this one has a pKa of 10.33. Like, it's still fairly acidic, but not as much as it would be if that O minus weren't causing problems. Okay, questions about those? Okay, cool. All right, so one other functional group we're going to look at a little bit here is something with similar factors affecting its stability, which is sulfonic acids. So we've seen some of these when we stuck them onto aromatic rings using EAS. So as a reminder, and I think the example I have in the notes actually shows it attached to an aromatic ring, because that's a very common context for these groups. But if we do the same thing that we did up here, deprotonate them, we get an O minus there, which we can then use resonance to bump around to any of 3 different oxygens. So we could bump it up to the top one, or we could bump it down to the bottom one. Okay. So not surprisingly, sulfonic acids are even more acidic than carboxylic acids, just due to even better resonance stabilization. So the pK of these groups, I think for this particular molecule, is about -3. But like before, you can dial that up or down a bit, depending on what other group you have going on. Okay. Questions about that? Okay, cool. So one kind of cool side note about carboxylic acids, if you deprotonate them, then they're called carboxylates. And they're pretty stable because they're not in a big rush to get their proton back. So you can actually have these sitting around as, you know, a carboxylate with a counterion. So it turns out that these are actually used as soaps very frequently. Especially if they have a long nonpolar tail. So the reason for that is you have some like long alkyl chain here. You have the deprotonated carboxylate, and usually the counterion to that is going to be like sodium most commonly. So this part is like a long nonpolar tail of the molecule. Which is what we would call lipophilic. It dissolves easily in fat or grease or nonpolar chemicals. While this thing is a polar head group. That dissolves in water. So hydrophilic. As opposed to fat soluble or lipophilic. Okay, so what this means is that if you have something that is greasy, like a plate or something that you're trying to scrub off with just water, obviously the grease is not very water soluble, it's not going to come off very easily. But if you put a little soap on there, what's going to happen is your grease droplet is going to have the tails of the molecule dissolved in it. So you're going to have this thing with a bunch of like tails buried into it with like the nonpolar head group sticking out. In the notes I draw the actual carboxylic acid part, but it's kind of too small to see on the printout, I'm realizing. So what you're doing is you're sort of converting the surface of the grease droplet into something that can interact pretty favorably with water. And so you're actually kind of solubilizing or dissolving the grease in the water, although you're not really dissolving it. It's still staying as a droplet. It's just had its surface properties changed. Okay, so this is called a micelle. But here's the water kind of surrounding the whole thing. But this is why soap actually gets things clean. It's because it can actually go in, break up the grease into little droplets that can then get carried away by the water. Okay. As far as where this comes from, it turns out fatty acids are a real common, like, traditional way of doing this. So that's why you can make soap by mixing ash from wood fires, which is mostly sodium hydroxide, with fat, which if you render it down just turns into a bunch of long-chain carboxylic acids. And then you make the soap by deprotonating the acid with the ash that you're using, and it combines to make soap. That's also actually why soap scum, if you have hard water, pops up a lot. It turns out like the sodium salt or whatever like +1 ions are pretty soluble and form micelles pretty easily. But if you have a bunch of like magnesium or calcium in your water, +2 ions are actually not very soluble. And so if the like calcium +2 comes in and replaces the sodium, then it just sort of coats out onto your bathtub or whatever. Okay, so questions about that? Okay, cool. So, with that all covered, so we've done naming, we've done sort of some bigger picture, like why are acids that way, and what kind of stuff can they do. So the next part of this chapter is largely review, but with some new stuff in it. How much time I got left? Okay, yeah, I got a while. Okay, so there are a bunch of ways we've already seen for making carboxylic acids. Okay, so we got a ton of options. Some of these are new, but they're sort of similar to stuff we've seen before. Okay, so probably I guess the most intuitively obvious one is just by oxidizing from something lower down on the oxidation ladder. So oxidation of primary alcohols or aldehydes. Okay, so we've already seen this from like the alcohol's point of view or the aldehyde's point of view. We know that you can take an ROH like this, and there's a bunch of ways to write that, but Jones is a perfectly fine way. And we can get an acid out of it like that. Or we can start at the aldehyde and do the same thing. Okay, so this is kind of probably your first choice a lot of the time. If you're not trying to change much about the molecule, you're not trying to make or break any carbon bonds, all you're doing is tweaking functional groups. So this one is kind of just a functional group interconversion is how we would look at this. Like it's nice and simple and easy to keep track of. Any questions about that one? Okay, this is like the third time we're seeing this reaction over the course of OChem, so hopefully it's not a shock. Okay, so we have seen another way that's a little bit more disruptive to do this, which is oxidation at the benzylic position. So let me actually write up here. This is just a functional group interconversion. So we're not changing anything else about the molecule. This one, oxidation at the benzylic position, we just saw a couple chapters ago. This one is notable because it actually breaks carbon-carbon bonds. Which may be what you're after, but maybe not. It's just one more sort of tool in your toolbox of things to do. So as a reminder, that one's going to look like if you take this and you do basically any of the oxidizing conditions from before, but in really harsh conditions, high temperature for a long time. I think the version we covered was KMNO4, but you can actually do it with a few other options as well. Okay, so what this is going to do is, so long as you have at least one H or OH at the benzylic position, this is going to snip off all other carbons attached to that position. So it's going to get you to that. Okay, so you've got to have at least some way for the oxidizer to get in there. We didn't really cover the mechanism because it's kind of not that relevant, I guess. Okay, questions about that one? Okay, cool. So another way to make acids that also makes or also breaks carbon-carbon bonds is from way further back. So ozonolysis. Okay, so this is also going to break alkenes in the molecule. Okay, so if you remember, there's actually two different ways to end ozonolysis. Like the step 2, you could do either DMS if you want to get aldehydes and ketones out of it, or you could do water and hydrogen peroxide. And actually the water is the only required part. Hydrogen peroxide just speeds it up. But if you do that, you're going to get 2 different carboxylic acids out of it. So like that. Okay. So those are the 3 that we've explicitly seen before. Any questions about those? Okay. Cool. So next up is a new one, which is notable because it makes a carboxylic acid and it actually adds a single carbon onto the molecule in the process, like the new acid carbon. Okay, so this is pretty close to something that we've seen before, but it's slightly different. Okay, so we know that Grignards will go after carbonyls, right? We've seen them go after aldehydes and ketones before. Turns out you can actually attack CO2, kind of the same as an aldehyde or ketone. So CO2, carbon dioxide, you can sort of think of as like a double carbonyl. It's got a carbon with a double bond to each of 2 different oxygens. Okay, so it's going to look pretty similar to when you used Grignards on aldehydes or ketones before. So how this will look is, so this is a way of adding a carbon. So whatever chain you have here, let's make it like, I don't know, a 3-carbon chain. You've got a Grignard. You've got your CO2 molecule. And this just goes in for the attack, just like in an aldehyde or ketone. And you get this carboxylate, which once you do an acidic water workup, you get a carboxylic acid out of it. Okay. So overall, if you wanted to write it out, it would be whatever Grignard, step 1, CO2, step 2, H3O plus, and you extend it by 1 carbon. Okay, so in practice, the way that you would do this is actually pretty cool. CO2 is kind of a hassle to deal with if you're dealing it with like pressurized gas CO2. But fortunately, you can buy dry ice really easily, which is frozen CO2. So what you do is you make your Grignard, you draw it up into a syringe, and you just like stab the syringe into a block of dry ice and shoot the Grignard into it. And it usually works pretty well. I guess the downside is we know Grignards react with water, and dry ice is pretty cold and tends to pick up moisture from the atmosphere. So that's why you usually go for the inside of the block. But then you get your Grignard reacting with CO2, and then you just do a water workup and you're done. So kind of fun and easy. Okay. So questions about that one? Yeah?
Does this also work with organolithiums?
Yes. As far as we're concerned for now, they're pretty much interchangeable with Grignards. Yeah. Yeah, we'll start to see differences between them like a little bit later on, but yeah, lithium's the same. So let me actually organolithiums. Yep. Okay, so the only real drawback to this method is that whatever your R is, it's got to be compatible with having a Grignard on it. So like it can't have any unprotected carbonyls, it can't have any OH groups or anything on it. So we're a little bit limited, but we at least know some workarounds like protecting group chemistry now that might make this feasible. Okay, so questions about that one? Okay, so one more new one that I'm going to cover in the like 5 minutes that I have left is also kind of a new combination of things, but they're all things that we've seen before, or I guess that's not entirely true. Okay. So another option is SN2 with a cyano group, so C triple bond N. Followed by hydrolysis. So I'm actually borrowing this out of the next chapter, but I think like to put together a comprehensive list of ways to make carboxylic acids, it sort of makes more sense to cover it now, and then we'll go into the actual mechanism later on. So C triple bond N, it turns out every one of those acid derivatives I listed in that ranking up there in the start of the lecture, if you react it with water, you can convert it back to its parent carboxylic acid. And we'll cover a lot more details and mechanism on that later, but just so we can see the overall reaction here. Okay, so we've seen SN2, but we haven't seen this hydrolysis bit. Okay, so if we take, say, whatever alkyl halide, and then we bring in sodium cyanide, do SN2, get that to that. And then hydrolysis, you need water. And because this is sort of the least reactive out of all the acid derivatives, it actually takes a fair bit of energy. So like heat and then acid or base. But eventually, you can break it down to the carboxylic acid. Okay, so just like option 4 here, Grignard's on CO2s, this is also going to add a single carbon to the molecule. And that single carbon is the carboxylic acid. So for number 4, the Grignard's one, the one limitation was that R has to be Grignard's compatible. For this case, the limitation is that whatever R is, it has to be SN2 capable. Okay. All right, so how much time I got left? Okay, I got 2 minutes, so let me actually cover the last one from this so I can start the next section. Okay, so the last one is just hydrolysis from any other acid derivative. Again, I'm actually borrowing this from the next chapter, but just to put it here in the one place. Pretty much any of the things on that ranking that are acid derivatives, so not aldehydes or ketones, but everything else up there. If you put it in water, it's going to convert to the acid that it came from. Okay, so things that are more reactive than acids, all you need is water. And that's it. You don't need to cook it or add acid or any sort of catalyst. It just goes straight there. Usually whether you want it to or not, this is basically why you don't leave the lid off the bottle of acid chloride, because it soaks up atmospheric moisture and breaks down over time. Anything less reactive, you got to heat it up. So like esters or amides, for example. You need water, but you also need heat and acid or base. And that'll get you back to the parent acid. Okay, so we're not going to cover the mechanisms for these until next chapter, but just so it's all in the one place and you know it's an option. Okay, yeah?
For the number 5,
Mm-hmm.
the notes you have acid column with your group, is that just a sulfate?
Yeah, so that's just like a polar aprotic that helps promote SN2. Yeah, thanks. Mm-hmm.